Okay. Hi, my name is Hyuk-Ju Kwon, and I'll be presenting my senior ocean engineering capstone project. My project was a one-way communication device via magnetic field. It was motivated by emerging underwater communication technology based on magnetic induction. Overview, I'll be talking about the underwater communication that's being used right now and compared to the magnetic induction based. And then how it works, there were three important stages of my project. First one was the coil design, and then conducting numerous signal analysis and achieving communication synchronization. And then I'll play a demonstration video and I'll talk about the skills I used and or learned throughout this project. So there's a growing interest in magnetic induction-based underwater communication due to its inherent advantages. So the current methods are acoustics and optics, but they're heavily affected by the underwater environmental conditions like temperature, salinity, and pressure. And they, for acoustics, they suffer from multipath fading, propagation delay, and they have audible waves, which in certain operations, it's easily detectable. And for optics, the water turbidity affects and cause scattering effect. And also got to worry about the ambient light. And also it needs a light of sight communication. So what magnetic induction based provides is a predictable channel response, which means those underwater environmental conditions does not affect how the signal propagates. It has a negligible propagation delay. It travels at a speed of light underwater, and it's also stealth. It has non-audible and non-visible waves. Note that this project was based upon or built upon an open source Arduino project called Wireless Magnetic Data Transfer by Tomi Chen. So the open source project only blinked an LED on the magnet sensor whenever it senses a magnetic field, and those magnetic field was induced by the user sending ones or zeros, and one indicating that magnetic field is on and zero off. So brief overview of how it works. So when a coil of wire conducts electricity, it generates a magnetic field. If you incorporate a switch into it, you can create modulation of magnetic field by turning it on and off. So with this concept, for my device, when a user enters a message, say a capital letter U, the ASCII binary code for capital letter U is alternating bits between zeros and ones. And so for this reason, I also choose capital U for my signal analysis and my communication synchronization test. But back to this, so capital U, the magnetic field would turn off, on, in that sequence. And my magnetic sensor, my Hall magnetic sensor is translating those binary sequence or binary code back to the user character. And it will display it on your computer. So basically the modulation of the magnetic field is used as a communication signal. So a little layout of my device. So you can send your message through your smartphone using Bluetooth, and the message will get converted into binary code by my microcontroller ESP32. And the ESP32 sends a digital signal to the relay module, that's my switch, and it will turn off and on the power supply to the electromagnet. And my Hall magnet sensor with the onboard microcontroller will display the message or decode, convert it back to the ASCII character, and display it on the computer. So my first stage was designing the coil, and there are three important factors controlling the magnetic field strength of a coil. There are the number of turns of the wire around the coil, the current, and the radius of the loop. So my design coil has 200 turns and has a radius of 3.45 inches and total resistance of 4.7 ohms. And using the resistance and supplying 27 volt, my current value came out to be 5.7 amps. So this equation you see here is a Biot-Savart law on magnetic field strength on the center line of a current loop. The BZ is the axial magnetic field strength on the z-axis. Mu naught is the vacuum permeability constant. R radius, I is the current, and Z is the axial distance from the center of the loop. So what I did is I multiplied this equation by the number of turns around the coil, and when you look at this equation with the set radius, I set it to 3.45 inches from the previous slide. Your current and the number of turn is your axial magnetic field strength multiplier. And because the current is also a function of the number of turns, because more turns you have, the higher your resistance is going to be, but it also results to higher multiplier. I was able to plot the Ni against the number of turns. And as you can see on this curve, it starts to level off after a certain point. So what that tells you is after a certain point, more number of turns, or every turn doesn't return the same result. So that point, I decided to be 200 turns because at 200 turns, approximately 88% of the multiplier is achieved. So now using 200 as n, I was able to plot this equation against the distance from the center of the loop. So the x-axis here, that's the distance, that's the value of z in this equation, and the y-axis is my magnetic field strength. And the blue line represents the theorized value, and the red dot is my measured value. They seem to line up pretty close to each other, and this also tells you and verifies that the axial magnetic field strength decays with the inverse cube of the distance in the near reactive field. So the second stage was conducting a signal analysis, and I conducted numerous signal analysis to gather important parameters that I needed to achieve communication synchronization. So the first analysis I did, I was trying to find out the signal to noise ratio values, and I conducted this analysis in 4 different distances: 2.5, 4.5, 6.5, and 7 inches. And as you can see, at 6.5 inches, the distance is between the transmitter and the receiver. So at 6.5 inches, the signal area starts to overlap with the noise area. So, but you can still clearly tell signal from the noise. So I decided to push my limit a little bit further. I went to 7 inches, and that is where I determined my the maximum effective communication range to be. And the other important parameters to achieve communication synchronization where I need to find the receiver's maximum sampling rate and also the rise and decay time of my magnetic field. Here, my receiver's maximum sampling rate is 83.3 hertz. This was conducted at 5 inches. I actually did multiple tests and all the from different distances, and the rise time and decay time were very similar. So in communication synchronization, the most important thing was implementing a communication protocol to my transmitter and my receiver. So this is my communication protocol. My transmitter will always send the trigger bit before it sends a byte. And then my receiver will always look for the trigger bit before it starts recording the bits of that byte. And then it'll go idle, uh, waiting for the next trigger signal to be received, to be detected. So using those signal to noise ratio values and rise decay time and the sampling rate, I was able to determine my bit duration, and my bit duration is 136 milliseconds. Bit duration is important because it needs to give enough time for each bit um, to fully develop to their potential magnetic field strength. So think of, and also following the communication protocol, you see the first group here is the trigger bit, and then I get the zeros and ones here for the whole 8 bits to the byte, then it goes idle. And again, I mentioned before, capital U was used for its alternating bit sequence. So, and you can tell pretty clearly which ones are ones and which ones are zero. There's a clear distinction, especially at a small or closer distance. But if I move it out a little bit further, so this one, I see 5 inches. It gets a little, you get more noisy signal, and you get a lot of jitters as well. And that could be from the coil getting too hot from running multiple tests, or maybe a mechanical delay on the switch. So what I did to overcome this noise was programming the receiver to take a moving average of the signals, 4-point moving average to be specific, to identify the start bit. Um, and then it divides every bit into 3 segments. And then it only registers the average of the middle segment of each bit. So the middle segment here is the shaded area. And then based on that average from that middle segment, if it's above the preset sensitivity level, it'll return a 1, and if it's below, it'll be a 0. And all the parameters I gathered from my signal analysis and then bit duration were used to write this program. So here's my final setup. You have my transmitters on the right side, a transmitter on the right side, and it's transmitting data through a fishbowl full of water. And that communication range was about roughly 5 inches. And you see my receiver, my magnet sensor with the onboard microcontroller connected to my computer by USB. This is a little demonstration video. Too, via Bluetooth. And my ESP32 is sending digital signals to the relay switch. That noise you hear right now is the switch turning on and off. And then on the receiver side, you'll see my message being displayed on my computer. It's loading on this computer. But yeah. So some of the skills that I used and learned, well, as far as technical skills, I coded my microcontrollers using C++ through Arduino IDE and Platform IO. And I used MATLAB for most of my plots, and I used 3D CAD, SolidWorks, to design my coil frame and some of the soft skills. I learned how to manage my time a lot better, especially with other classes that we all take. Trying to meet that milestone that I set for myself before the semester. It was crucial to meet those benchmarks. And then file organization, especially when you're programming, and also budgeting. Of course, my initial budget was a lot lower than my final. And what surprised me throughout this project and design experience was how effective flow charting your logic is when you're programming. Whenever I get stuck or confused coding, I went to the basics of CSC 101 and just got a scratch of paper and started writing down my thought process. And this really helped me to clearly help me write the program, especially for the receiver. So in conclusion, I demonstrated a one-way communication via magnetic field. I studied the optimal design of the coil and conducted numerous signal analysis for critical data in order to achieve communication synchronization. And this project served as a learning block towards understanding the working principle of underwater MI communication, such as the characteristics of electromagnetism, coil design, and communication processes. I'd like to thank Dr. Nudes, Dr. Mahdi, and my fellow classmates for their help and support. And I'll take any questions. Should I stop recording?
Oh.
Okay.
What is the maximum range that you're extending your receiver out to?
7 inches. Mm-hmm. I did some from 8, some from 9. I get few characters here and there, but I do miss a lot on just because the noise in the signal area is just too overlapped. So some of the
physical limitation.
Yes.
Follow-up question actually. What would you do to extend your range?
Extend my range.
The range of your communication device.
Multiple things. I can push more voltage in there, or I could redesign my coil to have more turns or have larger radius, so bigger diameter, or I can also use a different wire size. So yeah, that will all contribute to extending the range. And also maybe possibly a relay, like an extender, range extender. So I have another coil in between.